thing and sliced it there. Take it out, I'm still telling you it's a square, right? What would it look like compared to that one? It would just be smaller, right? So it'd be a small square. What about really close here to the edge? Slice through, it would be tiny little square, right? And then if I cut through the middle, big square, right? What's determining how long this square is? Or how the length of these sides? What's determining that? The distance between these two functions, right? So as you're in different places, it's changing the size of these squares. Do you all kind of have an idea of at least my verbal explanation of what this solid is? This is what its footprint looks like. And I'm telling you that when I take slices that are perpendicular to the x-axis, I get squares. The question is, what is the volume of this solid? What's its volume? All right, well, I'm going to show it to you first. I want to show you what this thing looks like. Because I'm trying to describe it to you, but I want you to see if you can see the actual picture. So here it is. Let me turn it into 3 space here. I'm going to come through here. I'm going to do squares. And when I cut through with squares, what I get is every slice let me make this a little bigger. Every slice that I make, right? Every slice I make, no matter where I am, my slices are smaller, right, towards the edge. My slices get bigger in the middle, and then back towards the other edge, they get smaller, right? All those are squares. If I were to put all those pieces of the cake back in, where the hell is it? There we go. If I were to put all the pieces back in, this is the shape we would get. That's what it looks like. That's a very weird shape, yeah? The question is, what's its volume? Well, how do you think we can figure out what the volume of this is? The sum of all the, not areas, you're close, some of all the volumes of all these squares, right? So if you could find a formula for the volume of one of them, you could then use the integral to add them all up, couldn't you? That's, again, we're using the integral as a tool. It's here to help us add things up. We just need to come up with a formula for this. Good? Now, we have to do a specific example, but this is just to get you to understand the idea. Now, let me change the problem a little bit. Same idea. I have a solid, different solid now. And what I'm going to tell you is that this is the footprint of the solid. Same footprint. But this time when I do these slices, right, and I take that piece out and I let you look at it from the side, they're equilateral triangles, not squares. It's going to be a different shape, isn't it? You'll have in the middle, you'll have a big triangle, won't you? Like instead of this, you'll have something like this, equilateral. It'll be like that, won't it? And then this one will be something like this. And then as you get closer to the edges, right, smaller equilateral triangles, smaller and smaller, right? Let's see what that one looks like. It's similar, but it's not the same, right? It's similar, but not the same. Do y'all see all the triangles in there? Let me back that out. See all the triangles, equilateral triangles in there? Oh shit, what happened? Didn't like that. Yeah. All right. That has a different volume, right? If we could come up with a formula for the volume of one of those triangles, then we could add them up and we could get the volume of the entire object. All right, different problem. Same footprint. Cut through, half circles, semicircles. Here's what this would look like. Okay? That's a different object, different solid. And so we would want to know what the volume of that is. So we move through here, right? We get semicircles, big circles in the middle, smaller circles at the edge. Now, in a class, in this class, we will only ever slice with a knife that's perpendicular to the x-axis or the y-axis. We'll never slice with some other like tilted line. And for me, I'm only ever going to do perpendicular to the x-axis, just to keep it simple. But homework problems, you might get one that's sideways. If you understand the concept, you should be fine. You should be able to develop the formula regardless. So how about we do the problem that was on the review for my students. That's not it. Where is it? Yeah. Let's look at number 4. We may or may not, yeah, I like this one. It's a little too big. I'll let you read that first. If you want, you can take a picture of it. It says here, the base of a solid is the region bounded by the first arc of the sine curve in quadrant 1 and the x-axis. Cross sections of this solid, cross sections mean when I cut it with a knife, that's a cross section. Cross sections of this solid, which are perpendicular to the x-axis, form equilateral triangles. First, draw the region and find an integral representing the volume of this solid. Do not evaluate the integral. All right. So I'm going to start off by trying to draw the base of the solid, right? This region right here, I need to draw that first for that problem, which I'm telling you is the region bounded by the first arc of the sine curve and the x-axis. So I'm going to do it kind of big here. Sine function goes like this, and then continues and goes down and back up, right? But we're only looking at the first arc of the sine curve in the first quadrant and the x-axis. So that's our region right there. This right here is y equals sine x, right? And the bottom of this thing is y equals 0, right? Is the bottom. Right, that's the base of the solid. Now, when I cut through and take a slice and go look at that slice over here, it's an equilateral triangle, right? So let me try and do that. If I take a slice, I'm just going to take an arbitrary slice like this. And when I take that slice and pull it out and bring it over here, it's got to look like an equilateral triangle. Equilateral, all sides are the same, right? That's what that means. If I could just find the volume of this, like a generic formula for it, then I could use an integral to add everything up. So when it comes to the volume of this, is there something that you at least know from like what we've been doing over the last, like since we started with areas and stuff? Is there anything you can tell me about that you know? How thick it is, right? How thick is it? dx. That's going to be dx because I know I'm going to be using an integral. I know I'm going to let that become infinitesimally small. So that thickness is going to be dx. Wonderful. Okay, then all you really need to know now is the area of that, don't you? If you know the area, then you know how thick it is, then you'll know the volume. So what is the area of that? Yeah, we want to find the area of this triangle, right? I'm going to put it in blue. We want to find the area of that. So if I give you an equilateral triangle, can we find the area? We'll get to that in a second. We'll get to that in a second. I want to make sure everyone's good, if anyone has any questions right now. I normally like to draw another picture with this. You don't have to, but it's a good practice. I try and draw it in three-dimensional space. So the way we draw in three-dimensional space is we draw an axis going vertical, and then you draw an X, but you make that X squash down. Like don't do this. It's very hard to draw in three-dimensional space if you draw like a normal X with a line through it. Squash that X down, then it looks like this. This is your X-axis, this is your Y-axis. And so what we're looking at is this, right? X and Y, we're looking at it kind of like like it's laid down on the ground. And so that the first arc of sine actually looks like this for us. Do y'all see it there? Do y'all see that that's laying down on the ground? It takes time to get used to drawing like this. What I did is I took a slice of this. Notice that the slice I'm taking is running parallel to the y-axis here. It's parallel. What I know is that when I do that, this creates a little equilateral triangle. So what I'm trying to do is draw that like three-dimensionally. Again, this is more of an option for you. Do y'all see how if I do a different slice down here, I get a smaller equilateral triangle? And if I do a slice over here, right, I get an equilateral triangle like that. See how, oh, that's too big, I think. It's not bad. See all those slices together is what we're trying to do? All right, feel good? All right, we need to know what the area of an equilateral triangle is. So I'm kind of pausing over here to talk about this. If I give you a triangle, and I tell you that that side, let's not call it X. I don't want to mix this up with anything here. Let's call this A. A. How about that? Or maybe I should have used B. Let's use B, because someone's going to say that's the base of the triangle. Sorry. Let's use B. Right? What's the area of that triangle? If all you know is this, all three sides. Well, we know for a triangle the area is what? What's the formula we all know? 1/2 base times height, right? We all know that formula, hopefully. So for any triangle, the area is 1/2 base times height. The drawback to that formula in this particular scenario is that we do not know what the height is, do we? Or do we? Do we know the height of this? Do you all see the height anywhere?
Would that be the arc?
Yeah. Wouldn't that be this? Wouldn't that be that top minus bottom? So we actually do know this height, don't we? Or do we? Are you sure? You need to make sure about that. Is that the height? Okay, so my picture is deceiving because it looks like this should be this, right? It looks like that, right? But remember where this picture is coming from, right? This is why I think this picture is worth like drawing. Because what is the actual base of this? The base is the actual sine, not the height. You see that? The base of that triangle is the distance, is this distance from here to here, right? That's the distance. So I actually don't know the height here. I don't know what it is. Is that okay though? If you don't know what height is, can you still get this? You could, I'm not. Yeah, there's probably some relationships that you could do. So what I'd like to do here, let's take a quick pause for a second. This goes back to pre-cal. I don't know how much your pre-cal instructor or Cal 1 would have stressed this to you. That when you have an equilateral triangle, this formula can be used. Yes, absolutely. This is good. However, for equilateral triangles, there's a better formula. And the formula that we can use is, I'm going to just draw it up. It's going to be off camera, but who cares? So if I give you a triangle, any triangle, doesn't even have to be equilateral. If I give you any triangle, and this is the height, and this is the base, then of course, yes, the area is 1/2 base times height. But there's another formula for area that you should know, especially as engineering, whatever else you're doing. And that is if you have an angle in here, theta, and you have this side A, that the area is 1/2 A times B times sine of the angle between the two sides. Now, most people don't know this formula. How many of y'all knew that formula? Maybe you've seen it in the past, but this formula, I think you should know this as much as you know this. For those of you going on doing more, right? You should know this one as much as this one. And here's you want to see where it comes from? It's actually very simple. It's a very simple formula to prove. Go to this triangle right here, and let me ask you this. What is sine of theta? Do y'all see a right triangle right here? Sine of theta by definition is what? H over A. Okay, solve that for H. Multiply both sides by A. Now, go to the formula that you're happy with, that everyone knows, right? And replace H with A times sine theta, and you get this formula. You see? So, what's the advantage of this formula? This formula says, in order to find the area of a triangle, instead of needing to know the base and the height, all you need to know is two sides and the angle between them. So if we go back here, right, if we go back to this, we know this side, don't we? We said the distance from here to here is sine x, right? And that's the bottom of our triangle. So we know that this is sine x, right? But since it's equilateral, so is this. So do we know two sides of a triangle? Do we know the angle between them? It's equilateral. So it has to be 60 degrees, right? So this formula is really nice when you have equilateral triangles because all you then need to know are the two sides, which are also the same, equilateral, right? So let's wrap this up. Let's wrap this up. For this problem, right, can you tell me the area of this thing right here? What is the area of that? We're trying to find that blue area. The area should be 1/2, okay? A times B, right? A times B, so the two sides multiplied together. What's the two sides for us? Sine x times sine x. So sine squared x times sine of theta, but theta is 60. So sine of 60 degrees. And what is sine of 60 degrees? Root 3 over 2. Square root of 3 over 2. So this area is going to be root 3 over 4 times sine squared x. So I'm using the fact that this right here is root 3 over 2, just from pre-cal, right? Root 3 over 2 times 1/2 gives you root 3 over 4, and then sine squared x. That's it right there. That's the area of that front face. Good or no? Questions? I don't know what's going on. All my classes, all of y'all have the same look on your faces right now. Like everybody seems like y'all are done, like burned out. Are y'all all right? Still got all of November. We haven't even started chapter 8. We haven't even started it. We need to find a second, third wind here. Get going. Yeah, margarita machine, exactly. All right, so look, I know what to do next. Do you know what to do next? We found formula for the area. Why were we trying to find the formula for the area?
For that one individual triangle.
For that triangle, we were trying to find a formula for the what of this? The volume of it, right? We found the formula for the area of the front, and we have the thickness. So can you tell me the volume of this one piece? Yeah, I'm just going to erase this. So for this slice, what's the volume of that one piece? The volume will be root 3 over 4 sine squared x dx. Okay, great. That is the volume of that one piece. Now I need to add them up. I need to add them up. So I'm bringing the integral, right? Okay, I'm going to do the integral. What are the things I'm adding up? The thing I just have right there, right? The question is from 0 to where, or from where to where, right? So you go back to your picture, right? There was that first arc of sine. Our rectangles are in here, right? Our rectangles are going to go start here, end here. 0 to pi over, is it pi? Pi over 2? What is it? 0 to pi, right? The first arc of sine. So this is 0, this is pi. So you just have to know that from the graph of sine. There it is. Okay? Whatever this is, right? Whatever this is. You could pull the constant out, couldn't you? And then you're back to sine squared. All right, I have enough time to do one more of these. Let's do the exact same problem, but this time, instead of our cross sections being equilateral triangles, let's have them be semicircles, half circles, right? Half circles.
So in the problem, when you're trying to like identify the shape of the solid, it's going to tell you it's going to be equilateral triangles.
Yep.
Or it's gonna be
The only things that I will ever give you probably is I'll either do equilateral triangles, semicircles, squares. That's usually what I like to stick to. But I believe there's a problem in the homework where they tell you that it's an isosceles triangle, and they give you a little more detail, so that one's a harder problem. But, you know, I try and stick to, for a test, I try and stick to like some basic shapes. For me, it's more about, do you understand the geometry? Do you understand like the visualization of what's happening, right? All right, so let's do it again. Let's do semicircles. So when I do it this time, I have the same first arc of sine here, right? I know that's 0 to pi. This is y equals sine x. All right. When I do my cross section in here and come look at it over here, it looks like a semicircle, half circle. And of course, it has some thickness to it, right? So I don't like the way I drew that. Oh, I don't like that either. Oh, I really don't like it. I'm having trouble. Okay, there we go. There. Something like that. Right? That's our semicircle. Now, how thick is this? That part you should always have dx. And then we just need the area of the front of it. Right? And that's a semicircle. So what's the area of any circle? Of a circle, a full circle? Pi r squared, right? So this is going to be half of pi r squared, right? Half of pi r squared. So you need to know the radius of that circle, don't you? But remember where this came from, right? This came from here, right? This is the base. Bless you. This right here, right? This right here is this base right here. So the radius, this red is actually the diameter of that circle, isn't it? We need the radius of that circle squared. So we just need to divide that by 2, right? Was there a question?
The z plane, is that would be the height?
Yes, coming kind of out of the page would be the height. You mean the height, you mean this piece coming up? Yes, it's coming up in the z direction. All right, so this right here is the diameter. So for us, the area of that is 1/2 pi. What's our radius? Sine x over 2, right? Because that's diameter, radius is half of that. And now I can just clean this up. This is 1/2 pi. Okay, that right there is going to be sine squared x over 4. And then I can bring the 1/4 out front, 1/8 pi sine squared x. That's the area of that piece. So the volume of the piece would be that times that, right? And then we use the integral to add them up.
Could you draw it the way you drew the 3D triangle?
Yeah, I'll do the 3D one. So I have my arc of sine here. And then I come through with my slice. I'll do it in red. My slice is parallel to the y-axis there. Right? And then I have my little semicircle that comes up and goes like that. And that's what all my little circles look like. That help? So we found a formula for the volume of each one of these. It's going to be 1/8 pi sine squared x times dx. And now we want to just move our rectangle across, right? Which basically moves all these semicircles, just to draw these little semicircles and adds up all the volumes as I do it. That's what that integral is. So integral goes from 0 to pi, and then it's just that formula. There it is. Whatever that is. And sine squared, right? So we could use that half angle or power reducing formula if we needed to. All right. We did it. We did it. So there's a problem. I'm not going to, because we have 10 minutes still, I'm going to finish class here, but I want to show it to you at least. Trying to think of where it is. There it is. So here's a common kind of like, when would you ever see something like this, right? So let's say that you have two pipes coming together, right? You can think of all different scenarios where this, whether it be metal or just like plumbing, like city sewer lines. I mean, you see these big pipes being put in the ground, different places around the city, right? Anytime you have two pipes come together, the question would be, what is the volume? What is the volume of that? What's the volume of this? Well, you can't just say, oh, you just take the volume of the blue cylinder and add it to the volume of the red cylinder and add those two volumes together, and that's the volume of those together, right? Yeah. Because they have a common intersection, right? You would be counting that twice, wouldn't you, if you just looked at them separately? So the volume of this, what you have to figure out is what part is common to both, right? You have to figure out whatever they have in common and basically take that out, right? Like if you just take the red and the blue, take their volumes, add them together, you then need to subtract whatever they had in common because you've counted it twice. So what do they have in common? Yeah, I'm gonna, that's too big. Can't see it. There we go. So what do they have in common? Well, I'm gonna just kind of fade this out of here. Do y'all see that that yellow section right there, that yellow section? There's 8 of these that they have in common. That's just one of the 8, right? There's that one. Let's look at it from the top. There's that one, and then here, and then here, and here. Wait, hold on. Maybe not. I need to bring them back in. I have them on the bottom as well. Yeah, we have, do you see this little piece right here? We have it here, we have it here, we have it there, and then we have them on the bottom as well. So we would need to figure out what the volume of that one piece is, right? So when you look at that one piece, that one yellow piece, can you tell me, if you look at it from the top like this, do y'all see that from the top? From the top it looks like this. From the top it looks like yeah? That's what that looks like from the top. And so you could say that this is like y equals x, and then you could say that this is y equals negative x, because it's a diagonal, right? So this is the footprint of your solid, right? That's the footprint of it. And now you need to talk about what the cross sections are. Like, what do all the cross sections look like? And then you could use what we just did. So we don't need to do it, but I'm just trying to show you, like, that's an application of it. And I mean, you may be saying, well, who cares, right, about the volume? But if you have like thousands of these types of connections, that's going to impact the volume, isn't it? Like, if you want to know the volume of your pipeline, then if you had thousands of these connections, you wouldn't want to like double count thousands of times. That would add up and you would be off a lot, wouldn't you? So, and then in Cal 3 class, what we do is we figure out, like, if you were to try and, in Cal 3, what we do is we figure out if you needed to weld, like if these were pipes you needed to weld together, we figure out the actual length of the arc that goes around these. We figure out what the arc length of that, and then then you can say, oh, that's how much needs to be welded. Anyway, okay. All right, we're done. So what do you need to do? 7.2 homework. Now, on your schedule, I do not believe there's a 7.3 homework. Let me check. There's not. Damn it. I forgot to send you all the homework assignment last time, and I told you I wouldn't forget. So, wow, we're a little behind, aren't we? We're a little bit behind, a lot of bit behind. It's all right. We will knock out the next section. We're going to actually start Chapter 8 next class. So not start it like beginning of class. 7.4, 7.5 are going to be very fast, 30 minutes, and then we're going to get in Chapter 8. So I promise you I will send you the homework this time. I promise, double promise, extra promise. The thing is, the book, 7.2 in the book is washers only. Washers and then these cross sections. 7.3 is shells. When I teach it together, like, you know, in one idea rather than two separate sections. But I need to add the homework from 7.3 so you can get some practice with shells. All right? So for now, until I send the rest, do 7.2. Try and do as much as you can there, and have a good rest of your week. Are we done? Yeah, we'll see you next week, right? Jeez, man, this is flying by. Okay. Turn off my camera real quick. I'm still on. If anyone needs to turn in the assignments that we're doing,